Yep, you need this. See that? That is our list of topics that we would need to be covering had we been together today. Now, this is for June 15th. However, it could be for any first day that we were meeting together, which we're not. So, okay. Anyways, you go to Essential Documents, you find topics for the first day of class. Look at it, download it. That's what I need to go over. That's what we have to make sure we covered. Actually, I've gone through a little bit of it. It says review gases at the top. You can see that. We already have a video on that, and I hope you watched that. All right. Okay, hang on. Oh, we got coffee today. Oh, do we have energy? Do we have energy? All right, so let's take a look at the next thing on here. It says intermolecular forces, first intramolecular forces. I'm going to go over that. I've loaded a couple of other videos in. If you just do not like the way I wear some sweet shirts, you know, I got some sweet shirts. You don't like my shirts, so you don't like my face. I mean, a lot of people don't. I don't blame you for that. I don't like it either. I never look in the mirror. And you just don't like listening to me, you get tired of it. Well, there are other videos which you can certainly watch, and I put a couple of them that are pretty good, but I'm going to go over some stuff that I directly want you to know. But there are other videos loaded as well. You have other options. Okay, I'm babbling, people, making like an ancient city and babbling on. I've already said that one. It's pretty funny, though. It's even better the second time. Okay, so intermolecular forces, that's what we're doing. Those are also called van der Waals forces. Any intermolecular force, you look on here, right there, you see it, you do. And it says intermolecular forces versus van der Waals. Intermolecular types of intermolecular forces, let's go over those. Those are called van der Waals forces. So a van der Waals force is anything that has to do with intermolecular. That means between different atoms or different molecules. You know, different compounds attracting each other. That's inter. Intra is within the molecule or the compound. Now, you should have had Chem 1, or you wouldn't be in Chem 2. I mean, that only makes sense. If you had Chem 1, you went over these. You did. You went over the different kinds of bonding, covalent bonding, ionic bonding. So you went over covalent ionic bonding. Yes, you did. And those are within the compound. So let's say that we have some good old high quality, made in America, H2O. And there is my Lewis diagram. We remember those Lewis diagrams. And a Lewis diagram shows the setup, the bonds, the single bonds, and the unshared pairs of electrons. So this water molecule, drawn with a two-dimensional Lewis diagram, has a bond here between the hydrogen, the oxygen, the hydrogen, the oxygen. That's an intramolecular force, or a bond. Intermolecular forces is going to be if I have a water molecule and I have another water molecule, all right, there's going to be an attraction between this positive hydrogen. Why is hydrogen positive? Because it's the metal compared to the very highly electronegative oxygen. So the oxygen is going to be pulling on the electrons from the hydrogen much stronger, therefore causing this part of the water molecule to become much more negative. And also because you have those two unshared pairs of electrons, it makes it a much more negative end of the molecule. That's what we call a dipole, or a polar molecule. Again, what I'm doing right now should be a review from Chem 1, so I do want to go through a little review here because it's, you know, it's important to understand what's going to happen today with the intermolecular forces. Okay, so the hydrogen ends up getting a positive charge compared to this very negative charge of the oxygen because of its strong electronegativity and unshared pairs of electrons. So what ends up happening is you have a generic dipole. The generic shape is that is an oval with a positive or a negative. And that would represent any dipole, anything which is polar. Water being polar, represented by that as well. So you will have a bond with another water molecule because there's a negative end and a positive end to each water molecule, and we all know it's a natural fact, opposites attract, okay? Paul Abdul, 1993. Yeah, check it out. I was going to say good song, but then I go, it's okay. It's all right. Okay, so you get this bonding occurring between, there we go, that's the intermolecular, between two different compounds or two different atoms even. you have this bonding which occurs. And I said between two different atoms. You might say, well, two different atoms, they bond to make a compound. Well, we'll show you later on what I'm talking about when I mean two different atoms having these weak attractions for each other. And these van der Waals forces, these intermolecular forces, the forces between two different compounds, let's say this is water between two different waters, they're relatively weak compared to the really strong bond that you have here, which is this is a covalent bond here with the water, but if you have an ionic bond, those are very strong bonds. Very, very strong. Stronger than the intermolecular forces, which hold different compounds together, which makes sense. I mean, if the intermolecular forces were stronger than the intramolecular forces, then it would tear the compound apart, which doesn't happen. So, you know, water molecule coming near a water molecule doesn't separate that water molecule into hydrogen oxygens. It doesn't happen because those bonds between the two different waters is weaker than the bonds within the water. So within the water or compound, Chem 1. Between, Chem 2, hence beginning of this course. All right, so there are different kinds of van der Waals forces. Let's go through them. Let's go through them. Let's rank them. Rank them, rank and file. Americans like to rank things, don't we? Number one, we're number one, we're number one. And then we'll go down from there. Okay, so now we know that the intermolecular forces occur between other things, not within. Then let's go through the different kinds. There are different kinds of intermolecular forces, some stronger than others. We're actually going to start with, I'm going to start with a medium one, but let's go with the strongest. The strongest intermolecular force is called a hydrogen bond. The hydrogen bond. That's the strongest of the intermolecular forces, the strongest of the van der Waals forces. Okay, those two are synonymous. They mean the same thing. That's number one. We're number one. So this is strongest. Then we have a medium strength one, which is going to be a dipole, or a dipole ion. Or an ion dipole, it doesn't matter. You say potato, I say potato. Actually, I never say potato. I don't know anybody ever has. Hang on, time out. Time out. More coffee. You're all jelly right now, aren't you? Yeah, I make coffee. Okay, all right. So these, actually, a dipole is how water bonds to itself, but there's a special dipole called the hydrogen bond. So hydrogen bonding is dipole. Now let's clear that up. Hydrogen bonding is dipole, but hydrogen bonding is special. Dipole, and we'll get into that in a little bit. The weakest, you are weak like the Ukraine, you are weak. The Ukraine is not weak. Seinfeld, okay, riding the bus, playing a little bit of Risk. George, he said Ukraine's weak, and the guy who was from the Ukraine on the bus heard that and said, the Ukraine is not the weak. Okay, just Seinfeld, good show, check it out. Okay, so the weakest of the intermolecular forces are sometimes called London. It was Fritz London. It was a person who discovered them. London dispersion forces. London dispersion forces. Now on the sheet I wrote, you can see arise within. And I only put dispersion forces on here, but where are we there? There we go. Okay, arise within. Now I'll go over that in just a second, what that means, arise within. And these, sometimes just called dispersion forces, but sometimes called London dispersion forces. Again, tomato. Okay. Now I have heard people say tomato. Okay, and those are the British people. Tomato. Okay. All right, let's start out with this one. Well, the medium. This is the weakest one. The weakest of these intermolecular forces. Okay. This, a dipole would be something which is a dipole. Let's say that we have I'll do the generic way of doing this. When you write a dipole, the generic way of showing a dipole is the oval with the positive and negative. If this is something just, and in fact, the dipole can cause what's called induced dipolism. I'll write that down. Induced What does that mean? To induce something means to make it do it or force it to do it. So if you can have a dipole-induced dipole, it doesn't matter if it's a dipole-induced dipole or the dipole which is connecting to another dipole. Okay, this is considered to be a medium strength. But an induced dipole, let me give you an example of that. So we've got something over here, just kind of hanging out, chilling like a villain yo. And it's not a dipole. Maybe it's, you know, something, let me give you an example, a little review from Chem 1. Here is a methane molecule, methane, the simplest hydrocarbon. This is not a polar molecule because the carbon, having a higher electronegativity than the hydrogen, pulls electrons toward the center. The hydrogen becomes positive. But the hydrogen being positive is positive all around. So you don't have anything on the outside that's a negative, you only have positives. And to be a dipole, you have to have a negative on the outside and a positive. You have to have two different ends. You have to have this positive and negative side, like the water had. This would not be a polar molecule because it only has positives on the outside. So I could not draw it as being a positive and having a negative. But sometimes things are non-polar. And sometimes things are nice and neutral, meaning that they have electrons and protons there, and power positives and negatives, and they're just kind of spread out evenly. But if you approach something which is either non-polar or nice and neutral here, then what happens is this negative side would force those electrons to shift. Electrons can move. The positives can't move unless it's in solution. Those would be where the nuclei are. But the negatives here can be shifted. They can shift. The negatives can move around. So we can force the negatives away because they don't like it. Remember, opposites attract, but like charges repel each other. So these negatives would run. They'd be like Sir Robin. Sir Robin, run away. Remember Sir Robin? I did not. Monty Python, Holy Grail, Sir Robin. Okay, good movie. So this negative here would force those negatives to shift. Now what did we just do? We caused this to become a dipole where it was not a dipole prior. Because now, since we've shifted the electrons away, we have negatives on the opposite side, and it's more positive on the left side, more negative on the opposite side. We've induced dipolism. And what would happen? These would attract. And there would be some intermolecular bonding or attraction there, some force holding these things together. So a dipole is when you have, and now it can be a dipole right off the bat and they'll attract each other, or you can do what's called induced dipolism, force something become a dipole and then it becomes attracted. Okay, then it could be a dipole ion. You could have a dipole like, you have a positive here and a negative here, and there's your dipole, and there's this ion. Maybe it's let's go positive. Maybe it's a sodium ion. So it's sodium ion, and it's just kind of hanging out there, chilling like a villain, yo. And then we can latch onto that one side and loosely hold on to that. That's what actually happens with water and sodium chloride when you put it in water. When you take sodium chloride, put it in water, the sodium and chloride ions dissolve and they're floating around. Floating, that's floating, by the way. And if I have a sodium ion floating in my water, here's my water molecule. Remember, I represented my water as a dipole. Showed you earlier the structure of it and why it is. Then that will latch on. The water will actually many waters can surround the sodium and the chlorine, and that's called hydration, where they surround it and keep the sodiums away from the chlorines in solution. But that's more on solutions. But I'm just trying to point out that there is, you dissolve salt in water, you get these positive and negatives, and they will certainly be attracted to the negative side of the water, or the negative ion would be attracted to the positive side of the water molecule. And that would be a dipole ion. So, intermolecular force. Okay. So those are considered to be, medium strength. They're not weak out of the three, but they're not the strongest of the three. Let's go to the strongest. We'll leave the weakest for last. The strongest of the intermolecular forces are what are called hydrogen bonding. Now, you're relatively intelligent, but You are relatively intelligent people. You know that a hydrogen bond has got to have hydrogen, right? Water is an outstanding example of hydrogen bonding in action. Water is hydrogen bonded to other water molecules in liquid water. So, and in solid water as well. They just kind of change shape a little bit, but hydrogen bonding. Now let's go back to the water. Okay, so I'm going to need some room here. So we're done with you. Done. I'll get to you. We'll come back to you. I'm going to switch to a nice purple marker. Sweet. All right. Hydrogen bond. Let's draw that water molecule once again. So water, okay. Water everywhere, not a drop to drink. Rhyme of the Ancient Mariner, right? We've all read it. It's an awesome poem. Actually, no, it's not. It's really long and boring, but whatever. Maybe you find it exciting. I just didn't. Sorry. Don't want to put my personal opinions in sway your brain. Water. Okay. Structure of water, we've gone over why it has a negative side to it and a positive side to it. This is more negative, you got more electronegativity, pulling electrons away, more electrons up here negative, and these lose their electrons, lose them, actually sharing them, but they don't share equally, lose them to the oxygen. All right, if I'm going too fast for you, I apologize. I mean, you can always rewind. That's what's good about these videos. It's called coffee, man. It's a coffee. Woohoo! Okay. So, so the hydrogen bond is right here. You got hydrogen, and it's bonded. The hydrogen's bond. There's your hydrogen bond. Wrong. Like in Family Feud, when you get the wrong answer, the X shows up on the TV screen. Wrong. But it was a good answer, because in Family Feud, whenever they give an answer, like, good answer. It doesn't matter what it is. It doesn't matter what it is. They always say good answer, right? Like, the question could be, name a vehicle that you drive down the road. Yes, a lamp. Good answer. It's not a good answer. I don't remember where I was. Oh, so the hydrogen bond's right here, right now. No, wrong. That is not the hydrogen bond. This is an intramolecular force or bond. We're doing intermolecular forces. So we need to have a hydrogen bond bonding to something else in a different molecule. Okay, so let's say we've got an oxygen here from another water molecule. Here's another water molecule over here. Here's a water molecule here. The hydrogen bond would be between the hydrogen of one water and the oxygen of another. And hydrogen bonding is a dashed line. Not a solid line. Solid line means a molecular or a covalent bond there. This is not a molecular covalent bond. It's between molecules, between two different waters, and we have the hydrogen and the oxygen. Hydrogen is bonding to something else in a different molecule, and we denote that by a dashed line. And of course, this would go on and on and on. Water is all, liquid water. All these molecules are, and here's another hydrogen. This would be attached to another oxygen up here, and so on and so on and so on. And now there we have water, which develops several characteristics of water that we are going to go over in the next video of why water does what water does. So, and water does a lot of things you might not even think it does, but it does, okay? And we're going to point those out. So there's my hydrogen bond. To have a hydrogen bond, you have to have a hydrogen, of course, hydrogen bond. And, you ready? It's important, because you will get multiple choice questions, and I'm going to see if you know this. And you have to have that hydrogen connected to one of these following three atoms. Nitrogen, oxygen, or fluorine. NOF. And I know you're saying, that's a NOF of this. that's a NOF. Dad jokes, good at them. NOF, nitrogen, oxygen, and fluorine. The hydrogen has to be bonded, intermolecularly bonded, to an oxygen, a nitrogen, or a fluorine of a different molecule. Now let me show you. I'll give you an example of one with nitrogen. So ammonia, here is ammonia, and I'm going to get rid of this water. We got enough water over there, you can still see it. The Lewis structure for water, as we all remember, is nitrogen with 3 hydrogens and 2 unshared pairs of electrons. All right, it's the unshared pairs of electrons that are important. Those are important. So you need to have unshared pairs of electrons to get the hydrogen. So here's a hydrogen from a different ammonia. And you know what ammonia is. It's what you get when you get sick. Okay, you catch ammonia. That's what you get. Yeah. And so this hydrogen is going to have that intermolecular force to a nitrogen, and it has that unshared pair of electrons, the unshared pair of electrons, and that's what you need, and it's going to form a bond to the different nitrogens. So the ammonia is going to be stuck together. And we're going to go through in just a minute what that means if we stuck together. This video is getting kind of long. I don't like videos that run over 20 minutes. I take this, the reason is how long they get boring. You kids are probably out there drooling right now going, in La La Land. And secondly, they take a real long time to upload, which is really annoying. Okay, so we're going to cut this one in just a second here. But so one question I sometimes will get, well, why is it got to be nitrogen, oxygen, and fluorine? Like, for example, if you look at the periodic table, just below oxygen is sulfur. Okay, sulfur, sulfur, sulfur. By the way, you do have periodic tables uploaded into essential documents, so you might want to grab one if you don't have one handy in a book or something. And take a look at it. Sulfur's here. So sulfur would have the same structure as oxygen, right? It'll have the same structure. Sulfur will have available to have 2 bonds and 2 unshared pairs of electrons. So why couldn't we get a hydrogen from another compound connecting to that unshared pairs of electrons of sulfur? It works with oxygen, right? Yeah, it does. Well, now the sulfur is going to form hydrogen bonds too, right? No. Well, why not? Because these are small. They're at the top of the periodic table. These are small. Nitrogen, oxygen, fluorine are relatively small atoms. Once you start going down here, you're getting larger and larger atoms, more and more energy shells. Okay, remember your quantum mechanics, energy shells, blah, 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 blah. And because they're so large that the hydrogen is going to be, from the other molecule, is going to be not close enough to form a strong bond. It can still form an intermolecular force adhesion. It'll be a dipole-dipole, but not strong enough because the hydrogen bond is the strongest of the intermolecular forces, and you need to have close proximity, smaller atoms, to that next door neighbor hydrogen in order to form a strong enough bond, which is considered to be a hydrogen bond. Okay, so whoever thought of that, Billy, was that you? Yeah, it was a good question. It was a good question. Why does it have to be these 3? It's because it has to. What it boils down to, it boils down to the size of the atoms. They're small, and they have that unshared pair of electrons. Okay, so that's hydrogen bonding. And remember, I will ask you multiple choice questions on an academic adventure about different kinds of bondings. I will ask you something like, hydrogen bonding occurs within the molecule. And of course, you're going to go, no. It occurs between different molecules, hydrogen and some other nitrogen, oxygen, fluorine of a different molecule. All right, that wraps up the first 2. We're going to begin the next video with the London dispersion forces. Okay, BRB, more coffee.